Welcome you all to the week 7 problem solving session of Basic Calculus 1. Myself Guru Bachan from Department of Mathematics, IIT Jodhpur. I am working in the broad area of fractal geometry and dynamical systems. In this problem solving session, we continue the Rolle's theorem and the mean values theorems problem, and then we will move to look first derivative and second derivative test for local extreme values for a function. So let us start with the mean value theorem, or you can say problem based on mean value theorem. Find the value of C in mean value theorem. First one is x square plus 2x minus 1, and the interval is 0 1. Second is x plus 1 by x, and the interval is half to 2. So we have given following functions and we have to find out the C values in mean value theorem. Now the first of all question arises whether these functions satisfy the hypothesis of the yes Deva. So first of all we have to decide here whether these functions satisfy the hypothesis of the mean value theorem or not. So let me recall what is mean value theorem. Let f be a function and let f is continuous on AB or you can say with f is differentiable on open interval AB, then there exists a C in AB such that this f dash of C is equal to f of B minus f of A divided by B minus A. Or diagrammically if I would say, then if this is A, this is B, this is the slope of between this A and B, A, B, this point will be A comma f of A, and this point will be B comma f of B, then the slope of this is nothing but the slope of the any value C. Suppose this is C, so these slopes are equal. So here we would need to first check that this function or this function is continuous on the given interval and these are differentiable on the open intervals, then we can find out the value of C. So now you know the value of this can say you know the hypothesis of the mean value theorem, and now you can easily find out the value of C. So First of all, try this at your own, then we will discuss it. So let us start. Fx is x square plus 2x minus 1, and the interval is 0 1. Clearly, f is a second degree polynomial in x. Therefore, f is continuous on 0 1, and f is differentiable on open interval 0 1. Thus, all the conditions of mean value theorem are satisfied. Thus, by mean value theorem, there exists a C in 0 1 such that f dash of C is f of 1 minus f of 0 divided 1 minus 0. So, what is f dash x? It will be 2x plus 2, and f dash c will be something 2c plus 2. So we will substitute this value in the above equation. F1 is, you can say, 1 square plus 2 into 1 minus 1. So this is 2. Whereas F0 is minus 1. So this will be 2 minus minus 1 divided by 1 minus 0, which will be 3. So 2c plus 2 is equal to 3, and 2c will be 1 and c will be half. So this is the value of c in first case. Now what about the second one? In the second one, given fx is x plus 1 by x and the interval is half to 2. Now the function here, this second term, can create a problem only at x equal to 0. But our domain does not contain x equal to 0. Therefore, we can say that it is a continuous function as well as the differentiable function. So clearly 0 does not belongs to half to 2. Therefore, f is half to 2, and f is differentiable on open interval half to 2. Therefore, there by mean value theorem, there exists a C from half to 2 such that f dash C is f of 2 minus f of half 2 minus half. F dash x will be 1 minus 1 by x square. Okay, now f dash c will be 1 minus 1 by c square, whereas f of 2 will be 2 plus half, that is 5 by 2, and f of half will be again half plus 2, which will be again 5 by 2. So from here, f, substituting these values in the above equation, we will get 5 by 2 minus 5 by 2 divide by 3 by 2. So this will give us 1 by c square is equal to 1. That means c can be plus minus 1. But minus 1 does not lies in half to 2. There, hence c must be equal to positive value of 1. So is it clear to everybody? Okay. Now let us move to the next question. Question number 2. Let fx is x if 0 less than 1, if then the function f is zero at x equal to 0 and 1, and differentiable on 0 1, but its derivative is never 0 on 0 1. How can this be? Isn't it contradicting Rolle's theorem? So we have given that our function is equal at 0 and 1, or else if you say f of 0 is equal to f of 1, and it is differentiable on open interval 0 1. So it has been, but its derivative is never 0 on 0 and 1, between 0 and 1. So it has been asked that is it possible or is it not contradicting the Rolle's theorem? So just first think and answer it, then we will discuss it whether it is correct or not. So if you recall that in Rolle's theorem, we need our function to be continuous over this closed interval and differentiable over open interval, and the first point functional value at first point and the last point should be equal to get the existence of f of dash is equal to 0. So here we have given that f of 0 is 0 is equal to f of 1. So from here I can say that the first point, the value at the first point and value at the last point of the interval is equal. Second, we have given that f is differentiable on this open interval 0 1. Now to apply or to guarantee the Rolle's theorem existence, what is the result of the Rolle's theorem existence? Rolle's theorem says that f dash c must be 0 for some c in 0 1 by Rolle's theorem. This is target, but there is one more condition we require. F has to be continuous on closed interval 0 1. If you will observe here, where the function is breaking at 1. So graphically if you will see, from 0 till 1 it is like this, but at 1 it is 0. So the function is continuous. Function f is not continuous at x equal to 1. Therefore, Rolle's theorem can't be applicable in this scenario. Hence, f dash c is not 0. So what is f dash c in this scenario? F dash c is 1, which is non-zero, because f dash x is 1. Okay. Now a similar kind of question to the mean value theorem is like this. For what values of a, m and b does the function fx is equal to b minus x square x is 0, x is 1, x is 2 satisfy the hypothesis of the mean value theorem, that is MVT, on the interval 0 to 2. So we have given a function and we have been asked that for which values of this a and b parameters this mean value theorem is applicable to this function on the interval 0 to 2. So try this. So if we recall the mean value theorem, then we must um, to apply this mean value theorem, our function must be continuous on its closed interval 0 to 2 and open interval 0 to 2. It must be differentiable. So just a second. So first of all, to maintain the continuity, our function is breaking at two steps, at 0 and at 1. And in between, at 0 it is a constant function, between 0 to 1 it is a polynomial, and 1 to 2 it is a linear function. So if you skip 0 and 1 point, x equal to 0 and x equal to 1, then our function is continuous everywhere between 0 to 2 except 0 and 1. So we need to make, or we need to check the continuity, maintain the continuity at x equal to 0. So what will be at x equal to 0? To maintain continuity, limit x tends to 0 plus fx must be equal to f of 0. And second limit x tends to 1 minus f of x must be equal to limit x tends to 1 plus f of x, which must be equal to f of 1. These things we want to make sure to guarantee the continuity of this fx on whole interval 0 to 2. So what this will give, limit x tending to 0 plus minus x square plus 3x plus a, and f of 0 we have given as 3. So from here this is 0 plus, and we know that this is a polynomial. Limit, first of all we substitute x equal to 0 plus h square, 3 into 0 plus h plus a is equal to 3. Next, 3h plus a is 3. So from here, since it's a polynomial in h, and we can directly substitute h equal to 0, so this will give you a equal to 3. Now from the other side of, can say, to maintain the continuity at 1, we consider this one. So limit x tends to 1 minus, that means we need to apply here, and x tends to 1 plus, we have to apply here, and x equal to 1 means we can substitute here. So limit x tends to 1 minus x square plus 3x. Now we know that the value of a is 3, and limit x tends to 1 plus, the function was mx plus b, and at m equal to 1, this is m1 plus b. So from here, 0 minus h square plus 0 minus x plus 3, limit h tends to 0 0 plus h plus b, and this is m plus b. So from here you can directly say it will be a polynomial in h. You can directly substitute h tends to 0. So this will give you the value 3. Oh, sorry. Here we are dealing with 1. So here it should be 1 minus h and 1 minus h. And here it should be 1 plus h. Okay. So when you substitute, this is a polynomial in h. When you substitute h tends to 0, this will give you minus 1 plus 3 plus 3, minus 1 plus 3 plus 3, and this will give you m plus b. So from here you will get m plus b is equal to 5. So this is one equation. Now to solve this, obviously this is an equation in two variables. We need one more equation. So now we can think about the differentiability. So if we'll recall, f has to be differentiable on this open interval 0 to 2. Here in 0 to 1 it is a polynomial, again 1 to 2 it is a polynomial. There is no problem. The thing is, the problem will occur at 1. So you need to make sure that limit 1 minus f x, or we may write it as h tends to 0, 1 minus h minus equal to f of 1 plus h minus f of 1. So if you will recall that the differentiability says that limit x tends to c, f of x plus c minus f of c divided by at any c. You will say that at any c. So this will be limit. It was correct. So h tends to 0, f of c plus h minus f of c divided by h. Or in general, if you will write limit x tends to c, f of x minus f of c divided by x minus c. So if you will think about the left hand derivative, it will be limit x tends to 1 minus f of x minus c and x minus c. So x will be limit x tends to 1 minus f of x minus f of c divided by x minus c. When you will substitute it x as 1 minus h, so this will give you 1 minus h minus f of 1 divided by minus h. So that's why we wrote like this. So now apply this to the given function. When we'll talk about 1 minus h, that means our function will be minus 1 minus h square minus 3 into 1 minus h plus 3. F of 1 is 5. We will substitute 0, you will get 5. So divide by minus h, and next is limit h tends to 0, f of 1 plus h minus 1. So for this our function will be m plus b minus f of 1, that is m plus b divided by h. limit h tends to 0. So from here, if you will observe that, you will get minus 1 minus h square plus 2h, and from here 3 minus 3h plus 3 minus 5 divided by minus h. Limit h tends to 0, m plus mh plus b minus m minus b divided by h. So you need to solve this. Just a second. Sorry for the interruption. So from here, if you will observe that, this will be left with nothing but this 5 will cancel out with this one, and you will left with minus h square minus h, that will be minus h minus minus 1, and since the denominator is minus h, so it will be h plus 1, and limit h tends to 0. From here h will cancel out, and bb will mm will cancel out, bb will cancel out, you will be left with only m. So this will give you m equal to 1. Now by equation number 1, you know that m plus b is 5, then b must be 4. Is it clear? So hence a is 3, m is 1, and b is 4 to apply the mean value theorem to the given function. Now let us do one question that is based on the application of Rolle's theorem. So it is like this: use Rolle's theorem to prove that between every two zeros of there lies a zero of nx to the power n minus 1, n minus a n minus 1 x to the power n minus 2 a1. So we have given a polynomial of this kind, and we have been asked to show that every two zero of this polynomial there exists a zero of this second polynomial. So this is a simple application of the Rolle's theorem. You just need to focus that what is the statement of Rolle's theorem, how we can apply this to this particular question. Try this one. So let us start this discussing this one. Since we want to show in this question, that is why I am writing at proof. So we have told that there are two zeros of this polynomial given. So let x1 and x2, or you can say a and b simply. A and b are two zeros of, before that, let p of x is dot 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 even x in R. Next, let px. So since px is a polynomial, therefore px continuous on this interval ab. Px is differentiable on an interval ab. P of a is 0 is p of p. Then by Rolle's theorem, there exists a C in AB such that P dash C is 0. That means, what is the derivative of this P dash x? The derivative of P dash x is n x to the power n minus 1 plus n minus 1 a n minus 1 x to the power n minus 1 a1 at x equal to c 0. So hence between, since c is between a and b, between every two zeros of a n minus 1 x to the power n minus 1 a1x plus a naught, there is 1 0 of n x to the power n minus 1 plus a1. Okay, now we will do two more questions, or in fact three more questions of similar kind, that you can be now easily able to prove how Rolle's theorem can be applicable, or you can say to get comfortable in applying the Rolle's theorem. Suppose that f double dash is continuous on AB and f has three distinct zeros in the interval thus show that f double dash has at least one zero in AB. Generalize this result. So we have been told that our f double dash is continuous over a whole interval AB and f has three distinct zeros in the interval. So we need to show that f has at least one zero in open interval AB and then we have to generalize this result. So try this one. So we have been told that f double dash is continuous on AB. So it is very obvious that f and f dash are continuous and differentiable on AB. So we can apply the Rolle's theorem. So let us apply it in two subparts. So cos f double dash is continuous on AB, therefore f and f dash are continuous on AB. So it's obvious the derivative is also existing, and we have given that it has three distinct zero f. So let let C1, C2, C3 be zeros of F. That is, FC1 is 0 is equal to FC2 is equal to FC3. And we may write it as FC1 is equal to F of C2. So now we can apply the Rolle's theorem to the interval C1, C2 and C2, C3. Apply Rolle's theorem on C1, C2 and C2, C3. So by Rolle's theorem, there exists some C4 from C1, C2 and C5 from C2, C3 such that f dash of C4 is 0 and f dash of C5 is 0. And we have been asked that we have to show that there exists at least one 0 in AB. So we have to discuss the zeros of double derivative. Now we can jump. Now we can apply. So it can be written as f dash C4 is equal to f dash C5. And we know that f dash is continuous on whole interval AB. Therefore, we can apply Rolle's theorem on C4 to C5 for f dash, which will imply then thus there exists a C6 between C4 to C5 such that f dash of C6 is 0. And C6, if you will observe that C4 and C5 f double dash, which is a subset of AB. So you have shown that f double dash has at least one 0 in AB. Is it clear? Now the next question is show that if f double dash is greater than 0 throughout an interval AB, then f dash has at most one 0 but if f double dash less than 0 throughout AB instead. Try this one. So let us show this. We have been shown that f double dash, given that f double dash is 0 for all x in AB. What is the meaning of this? That, wait a second. Okay. So here it is f dash, here it is f double dash. So think it as it is a function and it is its derivative. So if you will think it is an increasing function. So it will move like this. Or if it is starting from just here, it can go like this. Or maybe like this one or like this one. All the cases this is an increasing function. So diagrammically you observe that either it can cross at one point only or at nowhere point. So this is some kind of f1 double derivative, some kind of f2 double derivative, f3 double derivative. So I am giving you four possibilities kind of. There might be more in sense of increasing. So why this there is if why can there is a continuity maintained. Why I am saying that? We have given that f double derivative and f derivative. So it is a differentiable function. You will observe that. So differentiability guarantees the existence of continuity. Clearly, f dash derivative, that is f double dash, exists. Therefore, f dash is continuous on AB, and f, because f double dash x is greater than 0 for all x in AB, implies that f dash is increasing on AB. Since it's an increasing function, so hence f dash can cut x-axis at most one time only by location of roots. So if you will assume that it cuts two times, then can show the contradiction over that f is not, then f will not be increasing. So similarly, the result holds for f double dash less than 0 on AB. So that means here we also can guarantee that f dash can cut at most one time x-axis. Okay. Now the next question is, show that a cubic polynomial you no need to write this one, you directly can have at most three real roots. We need to show this one, and this is a kind of direct application of Rolle's theorem. Try this one, or in fact, there is no need of Rolle's theorem, I guess so. First try, then we will discuss it. So let us discuss this one. Since we want to show that there exist at most three real roots, so if possible, for that let us define the polynomial. Let Px is 4 real roots. Since Px is polynomial, therefore P will be differentiable and P dash x will be 3ax square plus 2bx plus c. Now we want to claim that it has at most three roots. Before that, there is one thing we missed out in the previous question. Let us first complete that. We need to generalize this one. Question number 5, would I say. So if f dash is continuous on AB, then f can have three distinct 0, then f double dash has at least one 0 in AB. So we want to generalize this one for, you can say, nth derivative. So what can we set that over it? What can we say? Anyone? What can we say over it? So for this we can say that if f has n zeros, then f dash has at least n minus 1 zeros. At least n minus 1 zeros, and f double dash n minus 2 zeros. So by the Rolle's theorem we know that between every two real zero there exists one zero. So here there are four zeros, four distinct zeros, you can say. So can we say that by Rolle's theorem P dash has three zeros? Now you know that this is a quadratic polynomial, and quadratic polynomial can have at most two zeros. So to be precise, we may write it like that. at least three zeros, but quadratic polynomial can have at most two real roots. Therefore, it contradicts our assumption. Hence, a cubic polynomial can have at most three real roots. Is it clear? Now we will do a question which has some subparts to apply first derivative test and second derivative test for local extrema of a function. So apply first derivative test to the following following functions. First one is f dash x is equal to x plus 2, f dash x is equals to minus 1 by 3 x plus t. Also discuss the intervals where f is increasing and decreasing and check your answers with second derivative test. Local extremas. So we have given three functions, three subparts. We need to find the local extremum of these functions with the first derivative test. Then we have to verify it with second derivative test also. In between, we need to discuss the monotonicity of these functions. So try this one. So let us start discussing this one. We have given that f dash x is x plus 1 whole square into x plus 2. So to discuss first derivative test, you can say that first of all we can recall f dash c is 0 or f dash c is not defined, then c is the critical point of f. One point is this, another point is f dash is greater than 0, then f is increasing, vice versa for less than 0. So we have given the derivative. There are two terms, x plus 1 and x plus 2. So if you will observe that, put, so this will imply minus 1 and minus 2 are critical points of f. Okay, so next is increasing and decreasing. Since these are critical points, so if we will observe that any sign after minus 2, sorry, I had drawn it a little wrong, so obviously minus 1 will be here. So any point after minus 1 will decide the function is increasing or decreasing over that interval. So if you'll observe that if you put 0 in this interval, this will give you a positive value. So that means after minus 1 the function is increasing. When you are between minus 1 and minus 2, you can put any point, minus 1.5 like that. That will decide the sign of your function. So if you will observe that x plus 1 is whole square is there. So obviously it will not affect any sign. It will anyway going to be positive. So you need to just think about this x plus 2. When you substitute minus 1.5, this will give you a positive value. So there is no change of sign. But when you come before minus 2, that is something minus 3. So this will be negative because this x plus 2 will be negative. Therefore, f is increasing on minus 2 to minus 1 union minus 1 to infinity. I am saying I am excluding minus 1 because I am assuming that strictly increasing, that is strictly greater than 0. At minus 1 f dash is 0 and f is decreasing on minus infinity to minus 2. Now how to apply this first derivative test? First derivative says that if your function is increasing and then decreasing, then the point is local maxima. Like this. Suppose this is your function. If your function is increasing, that is derivative is positive, and some way it is 0, then decreasing. So that means this is local maxima. Whereas also like the same will goes with this. Here f is not defined. Again a local maxima. In the same way, for local minima, the derivative is positive, then 0, then negative. Sorry, negative, then 0, then positive. So in case of not defined point kind of structure, you can think like this. This is negative, this is positive, and at this point this is not defined. Local minima, local minima. So if you will observe that there is a sign change from negative to positive and no sign change here. So since there is a sign change negative to positive, so therefore this minus 2 will correspond to local minima. Therefore x by first derivative test x equal to minus 2 is a local minima of f. Although minus 1 is a critical point, but it will not affect the sign. So it will not be valid for, you can say, change of sign or local minima or maxima. Next is B part, x minus 1 whole square x plus 2. So it is very clear that it is anyway greater than 0 except x equal to 1 and minus 2, or let me write it as minus 2 and 1. Therefore f is increasing on minus infinity minus 2 union 1 to infinity, and critical points are x equal to minus 2 and 1 are critical points of f. Next is the first derivative test. So it is minus 2, this is 1. Obviously it is greater than 0, so this will be positive and positive and positive. So there is no sign change of, therefore first derivative test is not applicable here. Before that, we missed one thing, that we need to also apply the second derivative test in the first question. So let us verify our conclusion with that also. So what is second derivative test? It says that if f double dash at critical point c is greater than 0, then c is a local minima point. If f double dash c is less than 0, then c is a local maxima point. So what will be the double derivative of f double dash x? Second derivative test. Let c be a critical point. So what will be the double derivative of this function? 2x plus 1 x plus 2 plus x plus 1 whole square, which will be x plus 1, and you will take x plus 1 common, so this will give you 2x plus 4 plus x plus 1, which will give you 3x plus 5. Now we will substitute f double dash 1 here, I mean minus 1 here, so this will give you 0. So at 0 we cannot comment like that. At 0 our test kind of failed. Similarly, now in this case scenario, so if inflection point, so here x equal to minus 1 is an inflection point. Next is x equal to minus 2. This will be minus 1 into minus 1. So minus 6 plus 5 minus 1, minus 2 plus 1 minus 1, which will be 1 positive. That means x equal to minus 2 is a point of local minima, and clearly it is the same as the first derivative test. So in this case scenario, f double dash x will be 2 into x minus 1 into x plus 2 square plus 2 into x minus 1 whole square into x plus 2, which will give you 2 times of x minus 1 x plus 2, and from here you will left with 1 x plus 2, and from here you will left with x minus 1. This will give you x minus 1 x minus 2, and this will be 2x plus 1. So when you will substitute f double dash at minus 2, so this will give you 2 times of minus 3 minus 4 and again 3. This will give you a negative value. Therefore, minus 2 is a local maxima point. Next is f double dash at 1. This will be 0. So this will imply x equal to point of inflection. So let us just recheck this calculation. So this is 2 into x minus 1 is equal to x plus 2 whole square, x minus 1. Okay, when you will take 2 into x minus 1 x plus 2 common, this will give you x plus 2 x minus 1. This will be 2x plus 1. Is it correct? It is correct. So now let us move to the C part. In C part, so put this will imply x equal to minus 2 and x equal to 0 is also a critical point because our derivative will not define at x equal to 0. So therefore we need to check 0, minus 2 and 0. After the 0, that is a positive number, function will be positive. before the 0, that is a negative number, minus 1, function will be negative because this will contribute as negative number, minus 1. F dash at minus 1 will be nothing but minus 1 to the power 1 by 3, that is minus 1, and here it will be 1. So this will be a negative number. And before the minus 2, be positive. F dash at minus 3, this will be some minus 3 to the power 1 by 3 into minus 1. This will be a positive number. Therefore, f is increasing on minus infinity to minus 2, 0 to infinity, and decreasing on minus 2 to 0. Now since there is a sign of change of sign, sorry. So by first derivative test x equal to minus 2 is positive to negative. Local maxima point and x equal to 0 is a local minima point. And when you will check with the double derivative, so when you will do that double derivative, assuming that x is not equal to 0, this will be minus 3 x to the power plus, so this will give us this will give you x to the power minus 1, or you can directly do this. We just need to substitute x equal to 0. Obviously x equal to 0 again it will not define, so the test will fail at x equal to 0. So f double dash at minus 2, this will give you minus 1 by 3, 2 to the power 4 by 3 with negative sign, and minus 2 it will be 0. So this factor will be ultimately 0. You can just say that at x equal to minus 2, this will be minus 2 to the power minus 1 by 3, which will be some negative number. You can say minus 2 to the power minus 1 by 3, that is a negative number. Therefore, by second derivative test, x equal to minus 2 uh, local maxima point, and at x equal to 0, the test fails. Because x equal to 0, the double derivative will not be defined, so we cannot discuss that point with second derivatives. So that's all from today's class. If you have any query, then you may ask. Otherwise, we will end this session here. So since there is no query, so thank you. Thank you, Deva.
Thank you, sir. Thank you very much, sir. Thank you all.
Thank you, Deva.